Okay, off we go. So here's where we were last time, picking up where we left off. So another tool for your toolbox of how to parameterize surfaces. Sometimes if you have an existing parameterization of a similar but importantly different surface, you can deform your existing parameterization to parameterize your similar but importantly different other surface. So here's my example. Let's recognize that the unit sphere is easy to parameterize, right? Rho equals 1, spherical graph parameterization, nothing to it, right? And so this I'm going to call is our existing parameterization. I've written it in sort of in vector form there. And then this is the exact same thing, just written as 3 separate equations. Take your pick, whatever. It's the same. Okay. All right. Now, we know that the ellipsoid with this equation and the sphere with this equation are very closely related. And in particular, the ellipsoid is what you get when you stretch out the sphere by certain factors. And you can see that, for example, in the fact that you get the blue equation by, among other things, replacing every x with x over a. Right? And then likewise the y with y over b, the z with z over c, like we talked about back in chapter 2. Okay, so having recognized that all we need to do to turn our sphere into an ellipse is stretch out the coordinates by these factors that we just noted. So here's an explicit doing of that. This formula for x right here, you can see it right there. And I have literally, to get my x coordinate of my ellipsoid, I have literally just stretched it out by this factor, that same a that you can see right here. I'm just multiplying the x coordinates, the former x coordinates, I'm just multiplying them by a, and that gives me my new x coordinates, and I have stretched by a factor of a in the x direction. Likewise, factor of b in the y direction, factor of c in the z direction. So anyway, like I say, that's just another way to think about it. Now, it's here's a different point of view on that same idea. Again, we know that we're replacing, for example, every x with x over a. Well, you can just do that right here in your equations, and your green parameterization will turn into your blue parameterization by just replacing the x with x over a. Right, so take your pick, you get down to the same result. Notice that in both cases, you have, for example, over here, this is actually x right here. Right? So that equation and this equation are the same equation, but they're certainly equivalent equations. Just a question of whether you where you put the a in some sense. It doesn't make any actual difference. Okay. All right. So very useful in some cases. And with that said, I'm going to remind you of one last thing. The book does have many more examples. The problem with the book's examples, at least as I saw them, is that they're all kind of the opposite of what they ought to be. They all assume that you have a parameterization, and then they say, okay, well, what is this thing, right? And I just don't think that's what your experience is going to be, right? As mostly engineers, and thinking back to my days as a physics major, I didn't get a free parameterization that I then interpreted. No, quite the opposite. I was given a surface by some description, and I had to figure out how to create the parameterization, right? So all the tools that I've showed you are for how to create a parameterization. The books are all the opposite. I like mine better. But of course, that's why I did them. Okay. All right, so this next page, there's some development on this page that is going through a bunch of details that I'm going to mostly just wave my hands at. So I'm going to do what I've done on a few occasions. I'm going to scratch out this entire page in the sense that we're not going to talk this through in class, and you're not responsible for the ideas that are represented only on this page. So you don't have to look at it if you don't want to. You are welcome to look at it, and if you want to understand the details of what we're about to do, then you probably ought to look at that, but you don't have to. Okay, I'm going to just jump straight down to here, and zooming back in, if I can get this to cooperate, here we go. If we have a parameterization of a surface, such as I have drawn here, now notice, of course, my surface in this case is the sphere, and that is an example, but think generally. Okay. So the idea is that parameterization means you have location as a function of your parameters phi and theta. Okay. Well, you can talk about what would happen if you were to move in the input space. So let's, for example, if you were to take off and start moving in the phi direction, right? Well, if you were to move in the phi direction in the parameter space, what do you think is going to happen on the surface? Well, you're going to move in the direction that phi indicates, and of course, phi would have us moving that direction. Moving sort of down a meridian, down a line of longitude, for example. And then likewise, if you were to move in the theta direction in your parameter space, well, then you'd be moving in the direction that theta points. You'd be moving along a line of latitude, for example. Okay. All right. So, with that in mind, and if a movement in either of these directions gives rise to movements in those directions, then geometric appeal, we can talk about a little piece of area in the parameter space, and we can talk about the resulting image piece of area over on the surface itself. And I can ask the usual question, which is, how much bigger is the output than the input? In other words, by what factor does that get stretched out? Why do we want to know what that factor is? Well, you can probably see this coming. We're going to want to eventually do a pullback. We're going to try to take questions pertaining to the surface and figure out how to rewrite them as questions that we can answer in the parameter space, because it's flat and it's going to involve double integrals and the things that we know how to do. All right, so what is that factor? Well, the punchline ends up being that it is this right here. That is what you multiply by your d phi d theta to get this image area ds. Now, where does that calculation come from? Well, this is a little parallelogram in space. Parallelograms have area, which is the magnitude of the cross product. Those edge vectors computed on the previous page that we're just going to skip turn out to be these. And again, you're welcome to take a look at those details if you'd like, and then factoring out the d phi and the d theta to give us what we need. So the punchline of this calculation is this stretching factor formula right here. When you're talking about parametrized surfaces, this is your formula for your stretching factor. So make sure to know this formula. This is definitely something we're going to be doing a lot of stuff with. Okay, having noted that, a little bit of notation and terminology we need to talk about. Let's see here. Let's do it like, see if I can, we'll do it about like this. That helps. Okay, so here's our stretching factor again. Let's talk about this vector on the inside. That's the vector whose magnitude is our stretching factor. That vector deserves a name and a terminology because we're going to be using it a lot. We're going to call it capital N, so momentarily just skipping down to this. Our convenient rewrite of this magnitude of the cross product of the partials of the parameterization, it's a mouthful, right? It's a lot to enunciate, a lot easier to say magnitude of capital N. All right. So the point being, this expression, the product of the partials of your parameterization, we're going to denote that capital N makes life easy in a lot of ways. Okay, so why n? Well, we call it n because it is a normal vector. It is perpendicular to the surface, and you can see that because it is a cross product of these partials, which are tangent vectors. Right? And a cross product of tangent vectors will give you a normal vector. So capital N is for normal. Specifically, I'm going to call this the parametrized normal vector. Let's see here. My picture is getting messed up here. Let me zoom in a little bit. Here we go. So this thing, I'm going to call this our parametrized normal vector. For the following reasons: normal, because it's a normal, it's perpendicular, that we've done that many times. Why is it parametrized normal? Well, look at the formula for it. Right? The formula for this thing, it comes right out of your parameterization. You take your parameterization x and take the partials and take the cross product, right? Process, but it comes out of the parameterization. So I think this is very reasonable terminology to call it the parametrized normal vector, given that that's where it comes from. For whatever it's worth, the book calls this the standard normal vector. I find myself uncomfortable with this terminology. Standard makes it sound like it's intrinsic to the surface. Very importantly, it's not. It's intrinsic to the parameterization. Right? But again, standard, the suggestions, the flavor of this word standard makes it sound like there's only one. And very importantly, there are lots and lots of parameterizations, all of which will give you different, always parallel to be fair, but still different capital N vectors. So heads up, the book is going to write standard. I'm going to be saying parameterized. Again, I like mine better. Okay. All right. So let's do something with it. We're going to compute now the area of the unit sphere. Now, you all know this formula from long ago, but what we're going to do is talk about one point of view on where it comes from. The very first thing I'm going to do is talk about parametrizing the unit sphere. And the unit sphere is easy to parameterize. Let's talk about where this came from. The unit sphere is really easy to write in spherical coordinates. Rho equals 1. So the unit sphere is a spherical graph. And this is just what you get when you do the spherical graph parameterization. Right, so now you're going to probably need to rewind, go back to Friday's lecture where we were talking about graph parameterizations, and we did an example of a spherical graph parameterization. Make sure you remember those details and make sure you are crisp and comfortable with how this is what comes out of doing that to the unit sphere. Okay, now computing as above, we take the appropriate partials. Let's see here, we compute the cross product. That gives us our capital N vector. Now I just waved my hands at a whole bunch of trig, right? Make sure you're good at that. Make sure you can do that, right? This kind of thing, being able to take partials with a lot of trig, doing cross products with a lot of trig, simplifying with a lot of trig, noticing when Pythagorean identities come up and allows you to streamline the way you write it. Very important, comes up a lot. Make sure you're good at that. This is what you should get. Okay, and then not quite done. That normal vector, its magnitude, that is our stretching factor, and this is another. I'm just going to kind of wave my hands at a bunch of trig, but make sure that you can do this, that this big nasty expression right here if you compute its magnitude, you'll get sine phi. Several Pythagorean identity simplifications come up in that process. It's, again, a healthy exercise. I think everybody should do this once in their life. And as I like to say, I've already done mine, and it's your turn, right? So please do fill in these blanks and make sure that you can do that. Okay, so what is all this about? Where are we going with this in the first place, right? So remember, what we're doing is we're trying to compute the area of the unit sphere. And the area of a surface, I'm going to kind of use suggestive notations here, but the total area is the sum of little pieces of area. If I were to chop up my unit sphere into little pieces of area, just add those up, that gives me the whole area. Well, we already know how pieces of area pull back. If I want to take pieces of area on the sphere and rewrite them in terms of areas in the phi theta plane, the stretching factor, magnitude of capital N, that's the stretching relationship between the parameter space areas and surface areas. And this stretching factor, as previously discussed, magnitude of capital N, we just computed. So we just plug in sine phi. We get a super easy integral. Again, single variable calculus, you all know how to do that. And we get the familiar answer we knew we'd get, 4 pi. So, nice little application. How are we doing? Is everybody with me? Okay. All right. I can get this to erase. Here we go. Okay, all right. So real quick summary. Generically, I was using a sphere there. It's kind of a familiar, nice to, when the opportunity presents, your first example would be something familiar. But in general, if you have some surface, a parameterization views points on the surface as functions of two parameters. Let's call them S and T. You can talk about little pieces of area with little position differentials ds and dt. You can talk about the corresponding little pieces of area over here and the stretching factor, and we've already computed all that stuff. Most of what you see down here is stuff we've already done. Our capital N vector there is this cross product. And really, everything else that's on the page is rewrites and stuff we've already described. So, in particular, that vector is the one whose magnitude is our stretching factor, right? A rewrite. Notice you can think of the capital N vector as having a direction and a magnitude. The direction I'm going to call little n. That's going to be the unit normal vector, what I'm going to eventually call the parametrized, again, because it comes from this vector, parametrized unit normal vector. So unit vector times magnitude gives you the whole vector. This is just a way of breaking that down into parts. And then also notice we can take this formula and rewrite it in coordinates. Now, why would we want to do such a thing? It's actually going to come up a little bit later. We're not going to do anything with it for the moment, but you can write that out in coordinates. You can crank out that cross product in coordinates. And what seems really weird, easily checked, but still pretty weird, pretty surprising, is that the coordinates that you get when you crank out the coordinate cross product of that capital N vector, really strange that its coordinates, you'll recognize this notation here. These are two-dimensional change of variables stretching factors. And why that would come up with a surface parameterization is really not immediately obvious. But there's ultimately a good reason for it. And I just wanted to get that onto the page. We'll come back and do something a little bit with that a little bit later on. Okay, now here is a nice special case I want you all to be aware of. I emphasize that this is a special case to support that that is a special case. I'm going to highlight the if here. So if you might happen to be using a graph parameterization. We like graph parameterizations. They're easy to write down, right? That is, in fact, if you have a graph, right? So if, not that you always will, not that you have to, but if you do use a graph parameterization, which of course is this right here, then the good news is they all kind of look the same. All graph parameterizations start with the parameters. Right? That's the big idea behind a graph parameterization, is that x is s, y is t. Okay? And then z is whatever that function is. So graph parameterization will always take this form, which means that the partial derivatives will always take these forms. Kind of convenient. Easy partials. Which means that the cross product, giving you the capital N vector, will always take that form. Which means that the magnitude will always take this form. And so this is a lot of work that actually we get to just kind of recopy at our leisure. Again with the if. Right, very big if. If you are using the graph parameterization, you don't have to do the partials and the cross products and the blah, blah, blah every single time. You can just go straight down to that formula. I strongly encourage you to memorize this formula. And as long as you stick with a rectangular graph parameterization, this is your stretching factor. No computation required. Now, another little convenience, you'll notice that all this business right here is the magnitude squared of the gradient. That's just algebra. And then you'll also notice and recall that the magnitude of the gradient tells you how steep the graph is. After all, we are talking about a graph parameterization. We are looking at a graph. So really nice fact. Not so much formula you're going to use a lot, but a nice little bit of intuition. When you're using a graph parameterization, your stretching factor only depends on how steep your graph is. You don't even technically need to know the function. You just need to know how steep your graph is. And I want to show you my favorite application of this little observation. So this is my attempt to draw a house with a roof on it. And let's entertain the possibility that you might want to put a new roof on your house, which I've been a part of several times in various different contexts, including fairly recently at my house. We had to put a new roof on the house. You got to do that every so often, 20 years or whatever. So here's the thing. Roofs are really expensive. Right? I mean, really, really expensive. Like, ballpark as expensive as maybe an entry-level car. Right? It's a lot of money. And how much it costs depends very heavily on how much surface area there is on your roof, and how are you going to measure that surface area, right? So you're just going to trust the roofer, right? What if he wants to, accidentally overestimate the area by a factor and then inadvertently accidentally overcharge you a couple $1,000 or something like that, right? That's not unheard of. Okay, well, so the way you're going to deal with that is you're going to check it yourself, right? You're going to compute your own area of your own roof. And here's the idea. That roof, you can see right there, is a graph, right? For any point down here in the domain, there is exactly one corresponding point on the roof. So it's a graph. And we can say we're going to use the graph parameterization. And we already know, we already know our formula for our resulting stretching factor is going to be that right there. And now here's the really convenient little construction coincidence. And that is, in many houses, not quite all, but in many houses, how steep the roof is constant. Surprisingly constant. And I don't really understand why this is. It's got something to do with, I'm sure there's good reasons. But it just tends to work out. The steepness tends to be about a constant. So I don't have to go up to my roof, risk falling off, and breaking untold numbers of bones, so that I can measure the dimensions of each one of these figures that makes up the faces of my roof. Right? There's a bunch, and this is a simplified scenario that I've drawn here. Right? My actual house has much more than the 6 faces that you see here. Right? My actual house has, God, I don't even know, probably like 15 or 20. And so instead of dealing with 15 or 20 hard geometry problems that involve me getting up and risking my well-being, right? I argue as follows, and that is, first of all, the surface area is this integral. There's my stretching factor. The steepness is a constant. That means that factor there is a constant. That means that my whole stretching factor, in fact, is all constant. Constants factor out of the integral, and all we're left with is adding up all of the xy areas. In other words, just looking at the area of the footprint. Right? It just works out really nicely. And the footprint area is much easier to measure. First of all, it's all rectangles. Right? That's the easiest thing on the planet to compute the area of is rectangles. So easy rectangles, tape measure as I'm standing on the ground, nice and safe. Right? And so a super convenient calculation of that footprint area. All I have to do is multiply by this little formula right here, where I do have to measure the steepness, but you can do that by going up to the attic. Right? That's much easier. And there you go. That computes your total area for you. Isn't that clever? I wish I could say I thought of this, but this was pointed out to me before I thought of it myself. Okay. All right. Nice little example. Okay, moving along. We're going to define a new kind of an integral. We've kind of already been doing a new kind of integral with the examples we were just looking at. But let's get it nice and generalized here. If you have a surface in space, right? So there's our two-dimensional surface. And notice, though, that it exists inside of three-dimensional space. If I want to make some sort of an accumulation argument, if I want to talk about, for example, as I always use as my first example, right, mass. If I want to talk about how much mass there is distributed across that surface, well, I can't use a triple integral. Even though it's a three-dimensional problem, I can't use a triple integral. There's no volume. It's a surface. It's intrinsically two-dimensional. Okay, well, so it being two-dimensional, can we use a double integral? Well, no. The double integrals are in the plane. This is not in the plane. This is sitting up in space and curving around, and all that curving stuff matters. So we do not have the right kind of integral to be able to address the question in general of how to make an accumulation argument over a curved surface. We just don't have that tool yet. What we do have is multiple models from which we can rip off the main ideas and write down, I think, a nice little formula right here, which is that. And the big idea, again, if we're talking about an accumulating quantity like mass, is the whole is the sum of the parts. And on any given little piece, like, for example, on this teeny tiny little piece right here, if I chop this surface area up into a bunch of little pieces, on that piece, there's a certain amount of area, and if I want to know how much mass there is on that area, I would say mass per unit area times area. Now, okay, likewise, let's suppose it's not mass. Let's suppose this is the side of a hill, and I want to know how many blades of grass total there are on the entire property on the side of the hill. Okay, well, that's a really hard question, but on any little piece, there's no problem. On a little tiny little piece, blades per unit area times area will tell me how many blades are on that little piece. So any accumulating quantity, anything where the whole is the sum of the parts, you take your surface and chop it up into little pieces, and you talk about stuff, quantity, whatever you're interested in, stuff per unit area times area, and that gives you stuff. And then, as with every other kind of integral we've talked about, you add up over the whole surface, and that gives you your answer. And so this now, of course, there's the big looming question of how to actually compute this, right? How do we actually turn the crank on this? We'll talk about that in a minute. But before we do, let's develop a notation for this. We're going to kind of steal, again, old notation. That summation we're going to represent as a double integral because it's ultimately two-dimensional. And the delta S, we're going to write that as ds. Again, just kind of borrowing notation. So we end up with this notation right here. This is what we're going to call a scalar surface integral, which I think makes a lot of sense. After all, our domain is a surface, right? So that makes sense. And notice furthermore that our differential is a scalar, our integrand is a scalar, and thus the name scalar surface integral. Y'all remember, I hope you remember when we were talking about line integrals, we made a similar case, and the very first line integral we wrote down, we called it a scalar line integral. And then eventually, after we had done several examples of real-world problems that work out to be scalar line integrals, we started writing down a different application. We got something that didn't work out quite the same, and we had to confess that we had a new thing called a vector line integral, and it arose naturally from a specific application, namely work. So that's going to happen here too. We're going to start off talking about these scalar surface integrals. We're going to do a couple applications, and then we're going to try a different application. Things are going to work out weird, and we're going to confess that we really ought to rewrite it, and the punchline is we are going to find a vector surface integral. That'll be coming up later today, possibly, hopefully, depending on how fast we move. Okay, so for the moment, scalar surface integral. How do we compute these things? Good news, we kind of already know how to do this. We already have this set up. All of this is old news from the last section that we just finished up. Right? If you have a parameterization, the formula for the stretching factor is the magnitude of capital N. That's what you multiply by input area to get output area. And let's see here if I can clean up my... Yeah, that's what you multiply by ds dt to get ds like this. Oh, and I forgot to put the ds dt. There you go. So the purple stretching factor from our parameterization is what you multiply by green to get blue. Like I say, that we already knew. And so sure enough, check it out, we inadvertently have already written down a computational formula for how to compute a scalar surface integral. If you want to compute a scalar surface integral, here you go. Notice you're just plugging in the parameterization right there. Notice you're plugging in your stretching factor previously discussed. Kind of nothing here is new. Very plug and chug. Let's see one in action. So here we go. We have mass distributed on this surface, the upper unit hemisphere, sort of the northern hemisphere, if you will. Mass is distributed with density given by that formula. Now, reminder, something to keep in mind, density, right? There's lots of different kinds of density. Not necessarily mass per unit volume. It's stuff appropriate to your context. Per unit size appropriate to your context. Here we have the mass distributed over a surface. Surfaces do not have volume. They have areas. So when I say that this is the density, from this context we infer this is mass per unit area. All right. Okay, so we want to compute the total amount of mass. We want to compute the center of mass. We want to compute one of the moments of inertia, blah, blah, blah. So a bunch of different integrals ensue. They all have a lot in common because they're all talking about the same surface with mass distributed in the same way, for which we're going to be using the same parameterization, and therefore, blah, 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 we're going to have the same stretching factor. A lot of the stuff is going to be, a lot of the details in these calculations are the same. So I'm just going to go through one of these. If you want to see the others, here they are. You can see the details of all four calculations are right here. We're just going to talk about the mass calculation. Alrighty, so here we go. Starting with mass accumulates. The whole is the sum of the parts, right? Reminder as well, mass is distributed across area. So mass on any given piece, mass is mass per unit area times area. And so notice very early on what we recognize is that it is a scalar surface integral that's going to answer this question for us. You want to compute the total amount of mass distributed across this surface. There you go, scalar surface area. Scalar surface integral. Sorry. Is everybody okay so far? All right, yeah. Okay, so from the previous page, actually here, let's zoom back in. You can see better. Here we go. From the previous page, there's our generic formula for surface area on a piece of surface. Note the stretching factor. Right there. Conveniently, we've already computed the stretching factor. The stretching factor is just sine phi. That's nice. Let's see, the density was given. That's right up here in the statement of the question. Density, for whatever reason, happens to be Z. All right, so we plug that in. Density is Z. All right, and the only thing left to be done is to figure out, wait a minute, what is Z? Anyway, reminder, this is one a lot of students get confused on. It is easy to lose track. Don't forget what a parameterization is. A parameterization is giving you position as functions of your parameters. And so in particular, if it's telling you position, the third coordinate of position is Z. And so right out of the parameterization, this Z is cosine phi. And off to the races. The mass that we wanted to compute, we've rewritten now as this integral. This is an easy double integral, already iterated, right? It's just a matter of cranking it out. And there you go. Does everybody buy it? It's very plug and chug. Okay. Next example. This is where things get weird. Kind of like they did when we were thinking about work. Now, just a reminder. We spent a bunch of time talking about line integrals. The very first line integrals that we ever wrote down were scalar line integrals. We were adding up mass. We were computing the area of a fence. right? Mass is just a scalar thing. There's no orientation with mass. Add up the mass in whatever order you want to add up the mass. Who cares? If you're going to paint the fence, it takes the same amount of paint whether you go around like that or whether you go around the other way. Orientation's got nothing to do with it, right? Then we started talking about work, right? And how did we compute work? Well, we have to confess that whether you go up the mountain road or down the mountain road, it's the same mountain road, but the amount of work that it takes really does depend. Uphill is hard, downhill is easy, right? So we're going to find something similar here. We're going to go into this next application kind of hoping, naively expecting that this will work out to be a scalar surface integral, and it's gonna get weird. So anyway, let's dive in. What I have on the screen here is all rehash. All of this is from chapter 3. You remember we talked about this thing called flux. It considers a scenario where you have an area and then you have a flow of a fluid, and if you know let's say for example the velocity of the fluid, then we can talk about the throughput or the flow rate, the volume per unit time passing through your surface. And the way we found that flow rate was with this formula here called flux. Okay, now please do recall there are two different scenarios that are reasonable. You might be interested in volume per unit time, in which case your vector field needs to be velocity. But you also might be interested in quantity per unit time or mass per unit time or whatever it is. And if that's the case, then you have to throw in an extra factor of density to sort of account for the fact that velocity doesn't tell the whole story. So separate scenarios, always make sure to keep an eye on which scenario is the scenario that you're in or the scenario that you're interested in, and make sure to get this correspondence right. Okay. All right. All old news. Here's the confession we have to start with. All of this assumes that your vector field is constant over the entire surface. What if it isn't? Not all vector fields are constant. Most vector fields that you will encounter in the real world are not constant. Right? Okay, so likewise, notice this assumes that your area is flat. It's not really very physical. Very often, what you're interested in is surfaces that are not flat. Right? Dare I say, usually. So, so what we've got to do is figure out how we can adapt to what if you have a non-constant vector field, right? So consider this vector field here. Check out how these vectors are all different. That vector field is not constant, right? And what if your surface is not flat? What if your surface is curved, like I, again, have here? No surprise. This is a much more representative, generic scenario to be concerned about. And the formulas that we have up there make no sense for this general question. Okay, by the way, you may recall, again, I like to flash back for comparison purposes, when we were thinking about work, right? We were entertaining the same situation. What if my force was not constant? What if the curve that I was following is not straight? Right? So this is a very analogous scenario, thinking about flux instead of work on a surface instead of a curve, but nevertheless, a lot of similarities. Okay, so first, ignoring stuff about orientation that I will come back to momentarily, there's a pretty simple approach to all of this, and that is we just chop it up into little pieces. Each little piece is approximately flat. Right? On each little piece, the vector field just doesn't have much time to change. It's just a small little piece. The vector field is approximately constant. And so, I mean, again, we'll come back to that orientation business in a moment. But on each little piece, this area, ds, and your vector field, f, at approximately constant and approximately flat, and flux on that piece is computed by our usual formula. Right? This is the chapter 3 formula for a flat, which this basically is, piece of surface with a constant, which this basically is, vector field. So on each little piece, there's nothing to it. Okay. All right. Now, before we write it all down, let's come up and let's address this little awkwardness, right? And this is where the things get a little bit complicated. When we talk about flux through a surface, which way? Right? What's positive and what's negative? So, for example, as I have this drawn here, right? You can see I have a surface. There's a vector field flowing through that. Would I call this flux positive or negative? What would negative flux mean anyway, right? Which direction should I use as my normal vector? I could, I suppose, use that as my normal vector, but there's no law that says I can't use that as my normal vector. Which one is right? Well, so the answer is that the person asking the question gets to choose, and there is no magic right answer. There's nothing intrinsically positive about up. Sometimes you need your fluid to be flowing down. That's how basketball works, right? The ball's got to go downward through the hole, right? You've got to indicate which direction you're going to consider the positive. Neither one is to be assumed to be, of course, naturally, obviously, the right answer. It's got to be said, right? So that is part of the question. That's something that's intrinsic to what we're going to call an oriented surface. You need an indication of what is the orientation, which direction is the positive direction through your surface. And it's arbitrary, but you've got to decide it before you can actually proceed to answering the question. Okay, so again, comparison purposes, remember when we were talking about work as a line integral, you had to decide, are we going up the road or are we going down the road? And you get opposite answers. You just have to pick which one is it that you're actually asking. Okay. All right. So with that orientation, that's what we use as our normal vector here. And we can write down a new kind of an integral on each little piece as previously discussed. That's how you compute how much flux there is through that piece. You add that up over the entire surface, and grand total, this expression right here is what's going to describe flux. That's how we're going to compute flux right there. Okay. Now, weirdness. Wait a minute. How are we? Okay, yeah, I've got a minute. Normal vector. That's an orientation. Orientation makes a difference. It's not like with mass, right? We're in this familiar situation. If we were adding up masses, there wouldn't be any normal vector. There wouldn't be any possibility of, oops, my mass was upside down. It's not a thing, right? So this is actually a pretty weird way to write that. What we're going to see next time, and I don't have time to go into this now, what we're going to see next time is that it really makes sense to group these two factors together into what we're going to call the ds vector. I'll make sense out of that next time. Notice, though, that having written it like so, notice that now we have a vector differential and we have a vector integrand, and this is our new, what we're going to call vector surface integral, and we'll pick up here on Wednesday. Y'all have a good one. See you later. Enjoy the eclipse if there's anything left, and take care of those eyes. All right. Oh, and again with the attendance, make sure that I mark you as present if I haven't already.